Okay, so is my screen visible to all of you?
Yeah, yeah. It is good.
Okay, so a few things I want to talk before I start the session. The session flow will be like this. First, we'll start with basic. What is PyTorch? What is PyTorch? What is Tensor? How we convert NumPy to Tensor? And then we will go towards implementing PyTorch in linear regression, logistic regression. And after that, we will go towards neural network. The scope for today is learning about PyTorch and learning how to implement it in neural networks and linear and logistic regression. For tomorrow, we are going to deep dive into deep learning models such as CNNs, convolutional neural networks, and text classification and multi-language models. And we'll see how PyTorch is implemented in them, how it helps us to implement these big models easily. Okay. So starting with my session of PyTorch. So this is PyTorch 101 introduction to PyTorch. So basically, what is PyTorch? So when we started machine learning to develop models, there were not such framework available at that time. So we used to take NumPy array or used to use NumPy or used to use array as a input or as a metric for our machine learning to be given as an input or an output. But then it became very tedious for us to make such models, make such big models like transformers and other like now we have Chat GPT. Even the GPT model is based on the transformers network. The when we stack the decode part of transformer, we get the GPT model. So for all these things, for all these complex things, we needed some frameworks which can do these things in simple single lines. So there were frameworks like PyTorch, TensorFlow, etc., which came into existence. With PyTorch, the with PyTorch, the advantage is it is more Pythonic. That is, if you write Python codes, you must have felt that Python is really easy to write than other coding languages. So it is more Pythonic. It is really very easy to understand PyTorch. It has very easy learning curve as compared to TensorFlow. And PyTorch has multiple support libraries for different audio, for different video. So so that's the reason we use PyTorch now. So other applications of PyTorch are computation and natural language processing. As I said, we have our transformers network, we have a Chat GPT model. All this is based on natural language processing. And when we talk about natural language processing, it is turning words into vector. And how we turn word into vector is using the word space, and we map every word into that space to a vector. And then we train our machine models. So in that also PyTorch can be used because PyTorch gives us very easy framework. Very easily we can implement models using PyTorch. The PyTorch was developed by Facebook AI Research Lab, that is fair. PyTorch emphasizes more on deep learning models to be expressed in diplomatic Python with Python. As I said, it is really Pythonic. Like it is very easy to understand what I'm writing as I go. It's not like Java or C++. Like we have to see things, sit and see things, figure out things, whether it is correct or not. Am I audible clearly and is my screen clearly visible?
Yes.
Is my screen? Okay. Yeah. So now going ahead. Now going ahead. Yes. Just a second. Missed. Yes. Yes. So then what PyTorch does is it allows us to convert the NumPy arrays directly into tensors, which we are going to look ahead as we go. We can use GPUs directly with PyTorch. Okay. And then PyTorch has dynamic computation graph. This thing is missing in TensorFlow. I will explain what this thing is as we go ahead. We will understand what dynamic computation graph is. It's basically, if I give an example, it's like assigning some space. What happens in Nesplace, it assigns some space for the things to be settled in. And what PyTorch does is it dynamically allots the space. So it is more efficient in doing that memory management that we say. It helps in automating computing gradients. So gradients computation is one of the most important thing while making a machine learning model, or to be precise, a deep learning model. Because when you compute the gradients, you compute the loss, then you tweak and tune your weights in the network. And by doing that, you learn things. So that is why PyTorch is important. Now going ahead. So as I said, it's a little really Pythonic, and then we have it has dynamic computation graph, as I said ahead, which is not present in TensorFlow. So it helps in allocation of or memory management easily than TensorFlow. Then we have then we have much support for power of GPU and accelerators in it, and then it is a replacement of NumPy. As you know, NumPy is not a framework for machine learning or deep learning. It is just a type which can be used if you want to build something small, and if you want to make something big, then you need PyTorch in it. Now, see, this was the thing that I was talking about. This is the power of PyTorch. Here you can see I have wrote torch.nn.rn. This is nothing but a recurrent neural network in just a single line, and I can pass the variables and the things here, and it can train a model for me. I don't need to write the whole model, whole RN model, what it is, how to write it. It can just be written in a single line. We have LSTMs, long short-term memories, which are much powerful than RNNs. LSTMs are used in captioning the images. They can also be used in this. They can also be used in giving the sentimental analysis of the sentences text in basically in neural natural language processing. RNS, on the other hand, deals with timestamp, time data. Then we have RNN cells, we have LSTM cells, we have then con 1D, con 2D. This is something we are going to look in tomorrow's session, in which we are going to deeply understand what is convolutional neural network. And there we are going to see this con 1D and con 2D. Specifically, we are going to focus on con 2D, which is convolutional neural network, which can be implemented single line. So this all things, this all power the PyTorch consists of just writing single line, and it can do many things with it. Okay. Don't worry about all these parameters, everything. As we go ahead, we will look into everything, and we will see how things work basically. Then we have loss functions. So see, these were the layers, these were the models. Okay, these are the layers basically of deep learning. You have these layers, you have these models. Okay, now seeing loss function. So first of all, let me explain you what loss is. See, if I predicted a price of a house X, okay, and the actual price was Y, then the difference between them is the loss. Okay, so there are different loss functions to calculate loss in such big, dense neural networks. Okay, so different loss functions, the MSE loss, which is mean squared error loss. We have L1 loss. We have cross entropy loss. We have NLL, that is negative log of loss and log. And then we have CTC loss. We have something called as, here it is not written, but it is we have something called as binary cross entropy. Oh, binary cross entropy is BCE is here. So these are the thing, different losses that we have. So we use these losses in computing the loss of deep neural network, and then putting them into a gradient descent, getting their derivative out, and then tuning our model, our weights basically. Now seeing pooling layer. Pooling layer is something which you will see in CNN, which we will see tomorrow. But to get idea of it is just like just like squeezing your image, just like finding the actual parameters which you want to find. Suppose that I have a big image, okay, a big dog image, okay, and I just want to find the part of the image where the dog face is. So what I will do is I will take the dog face filter, I will rotate it all over the image, and where I will find that, I will pull that in. It is just like pulling layer. So we don't worry, we'll see this ahead as we go. Then there are activation functions. There are different activation functions. Okay, so if I ask you a question that if whether 2x plus 3 is a linear function or a non-linear function, what it is 2x plus 3? Can anyone answer? 2x plus 3?
It is a linear function
Yeah, it is a linear function. So how can you say it is a linear function?
because of the arithmetic operations.
Yeah, because yeah, that is correct. But one more thing is that if I put any value of x, suppose I put x equal to 2x plus 3 only again, then so I will get a linear output. Okay, so that is linear functions. Okay, so it is very easy for us to differentiate between linear functions. Okay, like suppose what I'm saying is, suppose that you have a graph. Okay, and there are apples on one side of the graph and there are oranges on the other side of the graph. Okay, so what I can do is I can just draw a straight line between them. Okay, so I can differentiate between them. These are apple, this sides are apple, this sides are orange. Okay, but suppose I have something in which apples and oranges are mixed together. Okay, and then I have to figure out the line. So there I won't get a linear line, I will get a non-linear line. So for that thing we require activation functions. Okay, so there are different types of activation functions. So we have ReLU, that is rectifier linear unit. We have TANH, then we have softmax. This all things are different sigmoids we have. This all things are different activation functions. We will see them how we implement this in our models. Okay. So these are the different models. So we talked first about layers, these layers of R, which were RNA, LSTMs, GR, these are the layers inside it. And exact model, if you want to copy whole model as it is, like if you want ResNet 18 is a model, VGG 916. These are different types of model. You have to directly import them model. You can directly import them model using torch, using that models as models, and directly this all thing of this model, all the parameters of that model, everything, every tune things will be captured directly into your models. Okay, and then it can be used ahead. Okay, so with that, as I said in starting only, Torch has different support of audio. For audio, it has Torch text, it has Torch vision, elastic, so etc. It has. Okay, so let's not waste more of our time. These are references. The best way to refer is the documentation and the PyTorch own website. They have many things there. So this is there is also one GitHub repository which has fast PyTorch. You can also see that. So this is what is PyTorch, why is PyTorch, and what are different things included in PyTorch. Okay. So now what we'll do is now we'll move towards coding part, where exactly everything will be understood and where how things happening will be understood to you all. Okay. So first of all, what we'll do is we will start with basics. We'll start with Tensor. What is Tensor? How is Tensor used in PyTorch and other things? Okay. Okay. So is my this visible? Can anyone confirm? Is my screen visible for the IPML notebook collab?
Yeah.
Okay.
Yeah, it is good.
So now let's talk about Tensor basic. Okay. So there are two basic things that we have to do in Tensor. So first of all, let's understand why we need Tensor. Okay. See, when I am training a machine learning model using PyTorch, PyTorch is a framework for me, which is helping me in doing that. Okay. And PyTorch requires certain type of input and certain type of things, or certain type of calculations it has to do. Okay. So that calculations can be performed using NumPy. But for higher level, they are to be converted into tensors. So basically, you can understand as PyTorch require tensors to process. Okay. So what tensors are? They are just a generalized matrix or an n dimension or an n dimension matrix. Okay. So as you can see here, this is a 1D tensor. This is a 2D tensor. You just stack many 1D tensors, you'll get a 2D tensors. Okay. Then you stack horizontally, vertically 2D tensor, you'll get a 3D tensor. Okay. Stacking all these 3D tensors, you'll get a 4D tensor. Then 5D tensor, this 6D tensor. So this is the reason why we need tensors, because as you can see here, we are dealing in 6D tensors. Okay. So they can be 8D tensor, 9D tensors. There can be such big number of tensors can be there in our Google neural network model. Okay. So for that reason, we are dealing with tensors. Now, let's start with the things. For you all to access this IP1B notebook, what you can do is you can also code along with me if you want to, or if you want to just see here and then go, then try on your own things, you all can do that too. There's this GitHub repository, or the link I'm providing in the chat. There are all the GitHub, there are all the IPNB files of the today's session. Like I'm now dealing with Tensor Basic. So what you can do is you can go and open these files. I'm putting the link in chat. To everyone, chat is visible, correct? Chat is visible, correct, to everyone? If I assume it is visible. So you all can click on that link. You'll be redirected to this GitHub page. What you have to do is you have to just click on Tensor Basics. As of now, we are on it. You have to just come here and you have to just click on Open in Collab. As you click on Open in Collab, a copy will be created for you. Okay. So yes, so now start with Tensor Basics. So this is I'm here importing my torch module and NumPy module. This is my torch version, which is 1.131. Then now start with important things, like suppose I had a new NumPy array. Now I want to make a machine model. What I have to do is I have to first convert that NumPy array into a tensor, PyTorch tensor. So there are different methods. The first method is to directly convert that NumPy array into our tensor. So how we do is, see, this is my array. The type is NumPy array. Okay. What I will do is I will just write torch dot from underscore NumPy, and I will pass the array here. So what it will do is it will convert that NumPy array into my tensor. Okay. So when I print text, it is a tensor. Okay. This is a tensor data type. Okay. I got tensor printed, and the tensor data type here is torch dot int 64. Okay. Now, now to more to deep dive more on in the types. We are going to deep dive more into types, what are data types in tensors. But to be more specific, what you can do is you can just type x.type, then this will give you torch.long tensor. This type of tensor that we got here is a long tensor, it will say. Okay, now if suppose I want to, if suppose I had a very big numpy array, or suppose I want to convert a big numpy array into a tensor, the same thing we have to do. We have to first, what I'm doing is I'm just passing np.arange 0 to 12 and dot ratio 4, 3. That is basically making a metric of 4, 3 and 4 rows and 3 columns, and then passing values between 0 and 12 randomly. Okay. So sorry, array range. We are arranging values from 0 to 12. Okay, 12 is not included. It starts from 0 to and going till 11. Okay, and I have to just so I got this array, and the data type of this array is float 64. Hello. Yeah, sorry. I thought someone has any doubt. Okay, so if anyone has any doubt, they can ask. Okay, so now just converting this numpy array into a numpy array. Just pass this array here, torch dot from underscore numpy. As you pass the array, it will convert it into a tensor array. Okay, and the tensor type is double tensor. Yeah, so these are different tensor types. 32-bit integer, it's an int tensor. 64-bit long tensor. So we saw now long tensor and double tensors. Okay, now there is one problem with this type, torch dot from underscore tensor. When we do this, what is exactly happening is in the memory where my array is located, the same where the tensor is pointing. Okay. So what will happen is if suppose I change something in my array, then that will be changed in my tensor too. Sorry. So suppose you want to make a machine model, but it is inheriting from some numpy array, and that numpy array is changing, then your model will also change, or some different things might have with your model. Okay. So then if we don't want that, what we can do is we can use different functions like dot tensor directly. So see, we just saw torch from underscore numpy and as dot numpy, the as underscore numpy. These both are same thing that was happening. We can use these things differently. Okay. So now assume now, so now I'm explaining what I was saying. Okay, see, suppose I made an array of 0 to 5. Okay, 0 to 5, I have made array. I just I converted the array into a tensor, and I printed a tensor. So it is printed here. Now what I'm doing here is I'm just taking that array. I'm changing the value of that array second position 0, 1, 2. On the second value, I'm just putting 77. Okay. And then I'm printing t. See here, I printed t, the tensor I've printed. Okay. As I print the tensor, this statement, you can see even the tensor got changed. I have not touched the tensor yet. I have not touched the t yet, but still the tensor got changed because it is pointing to the location where the number array is saved. Okay. And so what we'll do is so if we don't want this to happen with us, what we'll do is we'll use torch.tensor array. So what dot tensor array will do is it will convert that array into tensor, and now if anything is changed in the array, it will not affect or reflect into the tensor. Okay. See here, I changed the array second position as 77 and I printed it. It came 0, 1, 2, 3, 4 as it was taken ahead before. Okay. Is this much clear? Is there any doubt till here? Any doubt till here? Anyone? Okay, I assume no doubt.
Hello.
Yes.
I wanted to let you know the chat is disabled.
Okay. So I assume that it might be due to it might be due to some settings. What you all can do is you all can go to GitHub. What you can do is you can go to SMLRA and you can type GitHub. And you'll be redirected to the you'll see this link SMLRA KGSC GitHub. You can click on this thing. And when you click on this link, these are our different sessions that we had. So you can come here, PyTorch 101 2023. This is the session that is going on as of now. You click on this, and then you can browse to the notebook that I am in, which I'm Tensor Basic. Okay, is that clear? Okay, so I assume it is clear. I will move ahead then. Okay, so yeah, so I was here. Now what we are going to say is going to say is little class constructors things. Okay, so see, I gave an array, no np.array 1 to 3. Okay, I converted it into I've converted into a tensor. It got converted tensor. I got 1 to 3 float. I got here float tensor. Okay, but there is small differences. So if I put small t here instead of capital T and then I run it, you can see the data type is different. The data type is long tensor. Okay, so this thing is also useful if you want to deal with something where you want low tensors or long tensors. What you can do is you can just put this t in different manner, capital V or a small t. Okay, it will change the data type for it. Same for here also. Same thing is shown here. Okay, and you can explicitly also say what data type you want for the array. So I put here data. I wanted torch.int. Okay, so as I run this cell, I will get int tensor. Okay, instead of float and long tensor, I'll get int tensor. So the default was long tensor if I put the small t, but here I wanted int tensor, so I got int tensor. So I assume this much is clear. So now we saw how we converted a numpy array to a tensor array. Okay. But what if I want to make a tensor from scratch? How to make a tensor from scratch? Okay. So what you have to do is there are two methods, that is torch.zeros and torch.ones. Okay. Now what is torch.zeros and what is torch.ones? Torch.zero says that I will make an array, I will make a tensor for you, which will be of zeros of the size that you give to me. Okay. And similarly for ones, it will make an array, it will make a tensor in which the n dimension tensor in which the elements will be one. Okay. So this thing is useful in initializing the weight of the network. Okay. What we do is we put random weights initially. Okay. So this thing can be used. Okay. So we can put zeros, we can put ones, or there are many other methods as we see down. We can put random numbers also. Okay. So what I did here is I wrote torch.zeros 4,3. 4,3 says that I want 4 rows and 3 columns, 4 rows and 3 columns, a metric of 4,3 with all zeros in it. Okay. And the data type was torch.int64. So I got this. Then I again made a n-dimensional tensor array, which is of 4 commas again, but of 1. So I got this. Now suppose I want to make a tensor from scratch of range. So there are functions as we has in Python, that is dot arrange. Arrange function, what it will do is it will create a array starting from 0, going till 18, not touching 18. Okay, but it is like open, like it is like something like this. Start from 0, go till 18, but the 18 is not included. Okay, that is till 17 only. It basically means still I have to go till 17. Okay, I have to go till here. So what I'm doing here is what it is saying is torch dot arrange 0 to start with 0, go to 18, and with the distance steps of 2. That is like start with 0, 0, then step of 2, 2. Then with the difference between basically 2 steps I have to take in between. Then 4, 6, 8, 12, 14, 16, and till 17 only we have to go. So 18 will not come. Okay. Now, so this is how we used arrange function. Then there is line space, dot line space function. What it does is it divides a line in the number of intervals you specify to it. And the line starting and the ending point you have to specify. So here the starting point of the line is 0 and the ending point of the line is 18. And I want to divide this whole line into 12 equal parts. So what it did, see here there are exactly 12 parts. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 parts are there. And the difference between all these parts are equal. So it divided the whole line into equal spaces. Okay. Now we'll look towards changing the data type of the existing tensor. So that is very easy. You have to just take the tensor, and my tensor was x, so x dot type torch dot in 64. The type was first float, then it is long tensor. Okay, so it just got actually changed into the long tensor. Okay. Now, as I said before, we were using zeros and ones. Now, if I want to use random numbers, I want random numbers in my tensor metric. Okay. So what I will do is I will use rand function dot rand. What it will do is it will put random values between 0 and 1 into my tensor and dimension tensor metric. And as specified here 4,3. So it is 4 rows and 3 columns and random values between 0 and 1. So you can see, as you can see here, there are values between 0 and 1. Okay. And then there is other type, that is rand n, randn. Okay. And this function, what it does is it is similar like rand function, but the difference is it has this. It is standard normal distribution. It gives a standard normal distribution. Okay. So where the mean is 0 and it's like a bell curve. You might have seen the bell curve standard normal distribution. So it gives the value from that range. So it is basically like this something. Okay. Then there is randint, which this is the function that is used most. And this is a random function. These two functions are used most in deep learning. What we do here is we basically want big deep learning tensor arrays in which we basically pass values starting from this to this. Start with the array size, and it gives us the value. And here is a random integer array in which I have to just pass the starting and the ending value, and I have to pass the size of the n-dimensional tensor. So it gives me this type T. Now there is something very important is seed, random manual seeding. Okay, random seeding. So this is very important in vanishing the gradients, which we'll see here. So what happens in a deep learning network is when you train a whole batch, okay, then you want to you want to flush out the gradient so it doesn't affect your next batch. It's okay if you don't understand what I'm saying. As we go ahead, we'll understand this. So what happens in a training of a deep learning model is we divide the whole data set into batches. Okay, we first put first batch, then the model learns something, and then we put the second batch, then model learns something. Okay, so what this learn something is happening is it is learning how to decrease the loss. Okay, so when it is doing that, there are some mathematical computations happening there. Okay, and there I want to flush out things. I don't want that to affect my second batch. So for that thing also we can use random seed, and for putting and we put biases, okay, biases in the network. Okay, and suppose I don't want that value of the biases to change, then also I can use random seed. Okay, so what a random seed does is, see, when I run this function dot red 2 comma 3, every time I will get different values. See, it is 0.9 0.6938 0.9693. Okay, so when I again run it, it comes 0.7 0.7041. Okay, but when I put this manual underscore seed, what happens is, as you can see here, the values won't change now. It is 0.4581. Again, it will be 0.4581 only. Okay. So if suppose you want that random values to sustain, you can use torch.manual underscore state. Okay. Now to this last thing, x dot shape to get the shape of this. Getting shape is very, very important. So because when we are training our deep neural networks, we put layers. Okay, we put number of hidden layers. So we need to understand what is the output of the previous layer to make the new layer and to put that data into the next layer. Okay, so what we can do is we can use dot shape function. So dot shape gives us the size of the. So here it was this x that we were using, the x that we divide. So the size is 2 comma 3. Similarly, I can use dot size also, that is equivalent to do shape. And then and there is one more thing, that is x dot device. So what happens in training is these models are very big, and suppose you want to what is happening in basically deep neural networking. So there are multiplications, there are some calculations going on inside. Okay, so when these things are going inside, you can use GPU, which is much more efficient in doing this, processing these things. Okay, so what we do is in deep learning, we put our model into GPU, we put our data into GPU, the batch data into GPU, and the rest of the other things we keep in CPU. Did you understood? So that extra device is useful to understand what type of device we are using. Okay, so this was just the basic of PyTorch. What is Tensor? How Tensor is used? Okay, is there any doubt on any question till now? Is there any doubt? Okay, I assume. Yeah, is someone asking anything? Okay, so I assume there's no doubt.
What is GPU?
What is GPU? What is GPU? It is graphic processing unit. So see, you have CPU, correct? CPU, which is mostly which is in your laptop. All laptops are equipped with CPU. Okay, but there are few laptops in which GPUs are there. Okay, what GPU does is GPU has this multiplication power basically, which can give results very fast to you. Okay, so you might have seen that you have very large CPUs now of 32 GB, 64 GB in your computers, but they are very small size of GPUs inside the computers. Okay, 2 GB RAM, 4 GB, max to max 8 GB in your laptop. So all these GPUs are so powerful that they can perform very high intensive tasks very fast. Okay, so that is GPU. We have one more thing, that is TPU. It is tensor processing unit. So when you see these all big models, but then our chat GPT only, if you take example. So these things use TPUs to train. That are tensor processing units. So this tensor processing unit, what they do is they do all these tensor operations very efficient and very fast. So that we can use tensor processing units. So as you can see here, my X dot device here is CPU. I will see you. I will show you how we can change this to GPU. We have this support in Colab of changing it to GPU, but there is some amount of GPU only available in Colab. Like there is limit in it. I will show you in the next thing when I go. Okay. So is there any other doubt?
Can you share this collab link?
It's all inside that GitHub. I think it might not be visible. if you all are on WhatsApp group, I will ask my team members to put the GitHub link in WhatsApp. Himanshu, Kedar?
Okay, sure. Thank
Yeah,
you.
yeah, I'll put the.
Okay, so now going to the next thing, that is tensor operations. Okay, then from here things are will become little more tedious for you. Then we'll go towards autograd and optimizers, and then we'll go to linear regression, logistic regression. Okay, so now let's understand what are operations we can do with tensor. Now what we know is, we know what is tensor, we know how to create tensor, we know how to convert numpy to tensor. Okay, now we are going to see operations on tensor. So I imported my libraries. Just start it. So if there are any cell, we'll stop. Okay, so see, basic slicing it is. Okay, see here, what I'm doing is I want this whole suppose is a array A. Okay, I want just this two numbers 3, 4. What I will do is I will just pass 0, that says the which row I'm in. So I'm the 0th row, that is this row. I want third to fifth, so 0, 1, 2, 3, third to fifth not included. So 3 and 4. So I got this value 3, 4. Okay, next is 4 to 4 to the end. This means this two dots meant till end, if nothing, no number is written after it. Okay, till end it says. So 0, 1, 2, 3, 4 here, and here 0, 1, 2, 3, 4 here. Syntax now this is this. So start from this, go to end, and both are same. So this is a square that I will get. Okay, so this is the square I got, 44, 55, 55, 54, 55. Okay, this is the square I got from here. Okay, then it is all numbers, or all the numbers of the second column. Okay, so 0, 1, 2. This is this is a second column. So all the numbers in the second column I want. Row is everything, and column is second. So everything in the second column. Okay. Now here it says is, now here there are two dots. Okay. So two, basically, I don't know the name. Okay, two things. So it says that start with second. So 0, 1, 2 start with here. Then there is this that says you have to continue to the end, and then there is 2 here that says on the step size of 2. So from here, then 2 steps, then down here. Okay, and then here this part says that you have to take all the second elements of it. So this element I will take, then is this element I will take, then this element I will take, then this element, then this, and then this. So this is what I will get as the output. Okay, so this is basically basic slicing and indexing. Okay, so now moving ahead. Created a tensor from 0 to 20 and reshaped it into 5, 4. Now reshape function, what it does is, if I just print this much, so I'll get a single tensor, okay, with everything inside it, okay, till 1 to 0 to 19, okay. But when I do reshape, what it does is it reshapes into the metric format. So it is 5, 4. So 1, 2, 3, 4, 5, and 4. Okay. And one more thing important here is, this values must be the this value must be the multiple of this. Basically, 5 into 4 is 20. If I pass any number here, suppose I just pass 3 here, then it will give me an error. Okay, because it is not a multiple of 3. 5, 3 is 15, and here I want 20 values, so I have to pass multiple value. Okay. So I got this. Okay. Now if I want this value from this, okay, this value I want to one output. Okay. What I will do is I will do X in the name 0th column. So 0th row and the first column, 0th row and the first column. So I got to one output. Okay. The second is X21, that is second row, 0, 1, 2, second row, and the first column. So this 9 value I got as an output. Okay, the tensor 9 I got output. Okay, so now it is now there is one more thing. It is start from 1, go till 4, and end with the step sizes, and the step size is again 1. So it says that start from 5, go with the step size of 1, so 5, 6, 7, and you have to go till end. So it will end here till 4. Sorry, till 4. So will end on 15. Okay, see, so it is start and step. This is start and then step. Okay, now reshaping the tensors. As we saw here, we use the reshape function. Same thing we are going to do here. Dot arrange, we arrange the function. Now if you want to reshape here, only what we can do is we can do shape 2, 5. So what will happen is you reshape in the 2, 5 function. 2, 5. Okay, just a second. So see, we got this output here. But if suppose I want to do same thing, what I can do is I can use dot view function too. What dot view function does is it views this thing in 2,5 into 2,5 structure. See, there are two rows and 5 columns. Okay. See, 5,2, if I do 5,2, then there are 5 rows and 2 columns. Okay. But there is same thing that is happening with X as we saw in tensor basics, which was happening with the from underscore numpy array. Okay. What was happening there is we were referring to the location. So the same thing happens here too. We are here referring to X. So if I put X dot view to comma 5, and if I change anything in X, then it will be reflected here too. So if I don't want that to happen, then what I can do is I can assign this to any other variable and then use it. Okay. This all things might seem very easy to you as of now, but when we go ahead, this all small things also will become very tedious for you to understand how this is happening, how that is happening. Okay. Then we use the view function. Then we saw the same thing that I was saying you about. So it must be reflected. Okay. So see, what we did is we just took the x dot view and just we replaced the first value. We replaced the 0 value with the 1. So 0th value was replaced with 1. And now I printed z. See, I didn't printed x, I printed z. But the thing happened with z was it changed. It changed because it was making the reference to it. So what we can do in that case is we can use dot clone. What dot clone will do is it will create a clone for this for z. So now if you change anything in it, it will give you, it will not change. See, if I print z again, the value of z is not changed. It came out to be 0 only. And here it was changing to 1. So I created a clone for it. Okay. Now we'll use inference technique, or like how can we see our array? Suppose that we want your tensor to be of size 2,2. Okay, but your tensor is very big and you don't know what the third variable must be, how this 2D array must be converted into 3D array, and you just know the 2 dimensions. What you can do is you can just pass that 2 dimensions the view, and the third dimension you can put -1. So what will happen is that -1 will be automatically calculated. That third dimension will be automatically calculated. So as you can see here, this 2 dimension is converted into 3 dimension. So they are 2 and 2. So see, this is 2 and such 2 columns are taken and this -1. So basically the third dimension is automatically calculated. The size is 2, 2,5. So as you can see here, there are total 10 numbers plus this 10 numbers. There are 20 numbers. So 5 into 2 into 2, that is 5 to the 10, 20. So the size is 20. So we didn't pass the last dimension. It automatically completed that last dimension. Similarly, dot view 4, -1. So I know that I want 4 columns, but I don't know how many 4 rows. I don't know how many columns it will take. So it's passed 4, 1. It automatically computed the last dimension and it gave out to be 5. So 1, 2, 3, 4, 5. Okay. Similarly, if I know the columns and I don't know the rows, so we can put -1, 5. So I just gave 5 columns and the rows will automatically calculate it. Now, it's the same here, random pieces. Now, one more thing. Now we'll see towards suppose I want to see some tensor as the other tensor looks like. So see, what I'm doing here is I just parts in X1 just stand 5,4. So a 5,4 random valued tensor in n-dimensional tensor was created. The second one is 2,10. So it is 2,10, which was created. Okay, 2 arrays and 10 values in each. Okay. So now what I want to do is I want to view this x2 as x1. So basically I want to reshape this 2 into 5. So what I can do is I can just pass x2 equal to x2 dot view as x1. So it will view as x1. So when I run x2, it will be given in the format of x1. The format of x1 is 5,4. So same way I got 5,4 here. Okay. Now squeeze and unsqueeze operation. Again, one of the most important operation when we will see ahead gradient descent, and when we will see how when we flush the gradients. So what happening in squeeze and unsqueeze operation is basically you can squeeze a dimension. Suppose I ask you, my tensor dimension is 2, 1, 3, 1. Okay. So there are the dimension is 4. It is a 4-dimension tensor. Okay. The dimensions are 2, 3, 4, 2, 1, 3, 1. Okay. So do you think that that 1 is making any difference in it? If I remove that 1, then so will it work or not? 2, 1, 3, 1. It is a 4-dimension. I will keep 4-dimension only, but is that 1 making any difference in it?
No, I guess.
Yeah, so it doesn't make any difference. So, so what we'll do here is see, we'll squeeze that, and what we can do in that place is we can use squeeze and unsqueeze operation. What this does is see, this is a tensor I passed. I printed a tensor, so I got shape as 2, 10. Okay, I got a shape. Now what I'm doing is I'm unsqueezing it. That is making it big. And how I'm doing is I'm putting one more row in it. Okay, I'm putting one more thing in it on the zeroth value. So see, now if I print this, I got 2 comma 1 comma 10. Basically, I got 2 comma 1 comma 10. Okay. So what I did was on the zeroth position, I inserted one more value. Okay. So I got 2 comma 1 comma 10. Sorry. It is 1 comma 2 comma 10. Huh, it got missed. So on the zeroth I'll put. Okay. So it is 1 comma 2 comma 10. Okay. Is it understood? And when I put on y comma 1, then I get 2 comma 1 comma 10. On the first position, if I put one more row, I put one more, then I get 2 comma 1 comma 10. Is it now understood? And when I put it on y comma 2, that is on second index, I get 2 comma 10 comma 1. Is it understood what unsqueeze operation does? It basically adds one more row in it, increases the dimension. Is it understood?
Yes.
Okay. So yeah. So now we'll move ahead. Now we will see the squeeze operation. So here is the squeeze operation directly. I will directly go here. So it is on the yeah. So I have y raised to y. I have y. Y is to take y. Okay. Suppose I have a tensor which has only one value, 4 inside it. Okay. So first of all, what I did is I added one more direction, one more dimension added on the zero. So it became 1 comma 4. Okay. Then what I did is 1 comma 1. Okay. So it is tensor 4. So value is 1 inside. So it became 1 comma 1. Okay. Then see here 1 comma 1. Then what I did is I added on the first position. So again it is 1 comma 1 only because both are values 1. What I did is I squeezed the row. I squeezed it into another dimension. So basically what I'm doing is I'm squeezing now. So my this one which was here, this 1 comma 1 will change it to 1. See, this 1 comma 1 is squeezed to 1. Only the two dimensions are converted into one dimensions. Can you see it? Is that understood? What squeezing and unsqueezing does? Unsqueezing basically add one more dimension to it on the specified location. If I specify 0, so on that 0th index, it will add one more dimension. Okay. And when I want to squeeze it, basically press it, what I will do is I will just pass the dimension. I will pass the index when I want to squeeze it. Okay. So it got squeezed. See, from tensor size 1 comma 1, it changed tensor size 1 dimension. Okay. So yeah, so basically this is also same thing, squeezing and unsqueezing. So you all can see that. Now I'm going towards the CPU and GPU thing. Okay, so now the thing that I was saying you in the before in tensor basics, how to shift tensors from GPU to CPU. So see, I created a tensor. It is a float tensor. My current device is CPU. What I will write is torch or device CUDA. CUDA is a toolkit which is used to access the GPU. Okay. In Collab, we get the GPU. If you go here in the runtime, sorry, in the runtime you go and you change runtime type. You click on change runtime type. You will get here none GPU and TPU options. Okay. So now as of now, I have clicked on the GPU. So when I see my first initially this was CPU. All these operations before were performed on CPU. And now what I want to do is I want to check if my GPU is available, that the operations I want to perform, all the other operations that I'm going to do should be performed on GPU. So what I will write is just dot device CUDA if available, if CUDA is available, else torch dot device CPU. As I run, I got CUDA. Yeah, CUDA is available. So it printed CUDA is available. What I will do is I will just write t dot to div. What I'm doing is I am moving. This was a tensor that I had. Tensor I had 1 comma 1 comma 2 comma 3. I'm moving this tensor to the div. Then the device here is GPU. That is a GPU. So when I done this, I can see that the device here is CUDA. That this GPU is used. Okay. And the type remains the same as it is. And suppose I want to again bring that thing from GPU to CPU, what I will do is dot CPU. So it will come from GPU to CPU. Is that understood? Is that understood? Okay, so I assume there is no doubt. I will move ahead. Now we'll see tensors arithmetic, basically how we add, subtract, multiply tensors. Okay. So again, from here, things will become a little more tedious as we go ahead. This all things will be used ahead. So now we'll see what is arithmetic operations, what arithmetic operations can be performed tensor. So we can basically directly add tensors. Tensor A tensor is 1 comma 2 comma 3, B tensor is 4 comma 5 comma 6. Okay. And I added it became 4 plus 1 5, 4 5 plus 2 7 and 6 plus 3 9. Okay. I got a tensor, 1D tensor of 5 comma 7 comma 9, value of 5 comma 7 comma 9. Okay. I can also use dot add function. if I use dot add function, I can just I can just put torch dot add, and I can just put two array which I wanted to add, two this tensor dimensions that I want to add, and it will be added and printed. Now suppose I want to do something. Suppose I want to do this. A equal to A plus B. What is happening here is it is adding A and B, and it is putting all the added value in A only. So how to do that is A dot add underscore B. So what is happening here is this operation is happening. Okay, so I print A. Here I print here I printed A. It was 1, 2, 3. Okay, so initial values of A were printed. But now if I perform this operation, A dot add underscore B, the values that will be printed will be 579. Basically this value. So it is just doing this operation A equal to A plus B. Okay. So these are different operations present, basic tensor operations: add, subtract, multiplication, division, modulus, power. Okay. We have absolute values also, torch dot absolute. If we have negative value, if we have anything that it will give a positive absolute value will give up to us. Okay. We have then reciprocal, square root. Okay. Then we have dot product. See, matrix multiplication is the most important thing. Even when we'll see CNNs, what we basically do is finding something in an image. We take a filter, we multiply, we start that filter, we place that filter on the top of the image. We start multiplying every element of the filter with the overlapping elements of the image, and then we see whether the value is high or not. If the value is high, then that element is present in the picture. Okay. So what I'm doing here is I'm declaring a tensor. We have declared two tensors A and B. Now I have just multiplied them. A dot multiply with the function that we saw above. So it got 4 in the 4, 1, 4, 5, 2, 10, and 6, 3, 18. Okay, I got this. Now if I do dot product, what I will get is I will get this operation. This final thing I will get. So if I add this all 4, 10, 18, I will get 32. Okay. So this was matrix multiplication as we saw above, and this is more in general matrix multiplication, how things is happening. So see here, here what we have is we have two metrics A and B, and this is B. As I said, if I have an image will be, suppose image is a 26,26 metric. Okay, I have a filter of 2,2 metric. Okay, the filter just has the pixels which corresponds to the face of the dog, and the whole picture has the whole dog image. Okay, and I want to find exact location where the face of the dog is. So what I will do is I will place that filter on the top of the image. I will go in sequence. I will find I will just multiply every pixels, and where I will get the highest value will be the pixel where the thing is happening, where the dog face is there. Okay. So what I did is I got the size of A, that is 2,3. I got size of B, that is 3,2. And as I know that matrix multiplication happens only if these two dimensions are same. The last dimension of the first one and the first dimension of the second metric. So there are 3. So I will get and the size of the metric that I will get is 2,2. This is that. So I got this. So this is torch dot matrix multiplication E comma B. Exactly the matrix multiplication happened. Okay. So this is A dot MMB. So same thing. Now here the matrix multiplication will store the value of it in A. Okay. And this thing will be used. Okay. That is all basic. And now element wise multiplication. So what we can do is we can have A dot mul, which can do element wise multiplication. Now here what we are doing is we are storing values of B dot B into A in B. Okay. So yeah, so that is all. Now something interesting we'll see, this is broadcasting. What broadcasting says is, see, I have a n-dimensional tensor array where we have this, okay, 3,4, and I have one more that is 1,4. Okay. Now suppose I want to add both of this. Whether we can add both of this, is it possible to add this and this? Is it possible to add both of this array as of now? Hello, can anyone answer how we'll add this both? Okay, can you answer? Is it possible if you assume like you are seeing two arrays, one is of dimension 3,4, and other one is a dimension of 1,4. So can you add both of them?
In theory, it should not be possible.
Yeah, it is not possible to add both of them because the dimensions are different. But what happens in broadcasting is, see, this is 3,4. This is 1,4. Okay. What I will do is I will repeat this T2 3 times, and I will add that on T1. Okay. So what I did is I repeated that T2 3 times thrice and I added it. So when you can do this is when you have this value as 1 only. Only when this value is 1, only that time it is possible. Okay. So it was 3,4 and it is 1,4. So I used this 3 times and I added to every row. I added to this and this. Okay. So this is called broadcasting. Similarly, we can do subtractions too. Okay. Now something interesting will see. Say this I have. The dimension is 3, 1, 4, 1. Okay. And suppose I give you this. Now say me whether I can add this to function. I can add T1 to and T2. 3, 4, 1. Is it possible? This is a 3 dimension. It is a 4 dimension. Is it possible or not? Okay, so I think it is a little confusing and difficult. So what I will do is I will make your life a little easy. I will shift this thing little here. Now see, this 1 and 1 matches. This 4 and 4 matches. This 3 and 1. Here it is 1. Okay. So what I can do is I will take it 3 times this. I can take this T1 3 times and I can do this. Okay, I can add or multiply anything, the operation that is set. So I can take this as 3 times and here it is 3 and here is nothing. So basically it means that I can directly put that put that thing here. So when I write T1 and when I write T2, it's print like this. And when I add them directly T1 dot T2, it can be added. And what output, the size output I will get is 3, 3, 4, 1. How this came is 1, I understood, 4 I understood. I took these size and I added on this, and this 3 came as it is. So it is 3, 3, 4, 1. Understood? Is there any doubt in tensor operations and slicing indexing as of now, and moving how to move the tensors to GPU and CPU? Is it clear? Is it clear? Okay, I assume there is no doubt, so I will move forward. Now from here, things will become a little tedious. Now what we are going to learn is what is gradient descent, how to implement it, what are different types of passes. Okay, just a second. Yes. So starting with, see, when we see, suppose this is a neuron, okay. So what is forward pass? See, I have value X, I have something value Y. There is some function which is performing some operation, suppose addition operation only, okay. What I do is I put X plus Y, I get the output Z. Okay, this is my computed output. And suppose there is something output W also present, okay. And that W is the actual output. What I will do is I will do X minus W. And that the difference that I get is my loss. And I want to decrease that loss. Okay, so what basically forward pass is just to put the values into a function and to get the output. Okay, now what is backward pass? See, I calculated the difference between this Z, which is calculated, and the W, which is real. Okay, when I subtracted them, I got something. I got some value, and that value is my loss. How much distance is there between me and the real value? Okay, so what I have to do is I have to tune this weight. I have to tune this X and Y. Okay, here these are there. Here, if I treat them as a weight and not as input, I have to just tweak them. Okay, I have to change these values of X and Y. So I will get Z, which is equal to W, or which is more or less equivalent to W. Okay, so how to do that? So what I will do is I will calculate the derivative of that loss with respect to Z. So see what I'm doing is I'm calculating derivative of that loss with respect to Z. So when I did dl by dz, I will change. I basically got the curve. Okay, steep learning curve. How much difference is there? Okay. So what is dz here? Dz is nothing but dz is nothing but it is combination of X and Y. Okay, this is some function which is giving me dz. So suppose I want to correct dz. So for that correcting z, I have to correct X and Y too. So it is a chain rule. I want to correct dz, so it will be dz by dx. It will be dz by dx, dx and something like that. Okay, it is a chain rule which we will see as we go ahead. So similarly, I have to change y too. So this is backward pass. So again, I will explain what is forward pass and what is backward pass. In forward pass, what we do is we give input to the neuron. We give input and and every of this line has weight, corresponding weight should. Okay, for simplicity, just assume we give some input to neuron. The neuron computed something, it gives some output. The output that we got is, suppose, 10 unit is a 10 unit distance from the real output. So this 10 is my loss. This is my difference which I want to decrease. So for decreasing this loss, what I will do is I will change the value of my inputs. I will tweak my input in such a way that I get minimum loss. Okay. So this is forward and backward pass. Is it clear what is forward and backward pass? Is forward and backward pass clear? Okay, I assume it might be clear. Maybe. Is it clear?
Yeah.
Okay. Now moving to gradient descent. What when we are when what I said what here is happening is dl by dz. Basically, when we are computing computing the derivative of the loss with respect to weight, what is happening is, see, something like this. This is the place where my gradient will become zero. Basically, my loss will decrease. Okay, my loss will become theoretically zero. Okay, and here I am somewhere. Okay, so what I will do is I will try to come to this point where my loss will become zero. Okay, so this is what this all this climbing is called. This coming down is called gradient descent. We are descending towards the minimum value, the minima value. Okay, so this thing we have to use in our deep learning models too. So similar thing happen in deep learning models also. So suppose you give some input, there's some predictions happen, then these predictions are not exact correct. So what we do is we tweak our model. We use optimizer functions in it. What optimizer functions do? They basically try to optimize the model. How they optimize? They change the weight of every input that they have. Okay. So one more thing that is very important for us to learn is learning rate. What learning rate is? See, learning rate says how much big steps you should take, or how much. See, this lines you are seeing it. These are basically steps. I jump from here to here, then I jump from here to here, then I jump from here to here, then I jump from here to here. So learning rate says that how much this jump size must be. So see, there are two problems. It can't be very low, it can be very less, and it can't be very more. Okay, very high. Suppose it is very small. Okay, the learning rate is very small. What will happen is it will divert, it will converge very slowly. But it basically it will descend very slowly. So when this thing will happen, my computation power might run out. Okay. And when I have very big learning rate, what will happen is it might miss this minima point. It might go in some other direction. Okay. So that thing can also be happening. Can also happen in that. Okay. Now we understood what is gradient descent, why we need gradient descent, and what is forward pass and backward pass. Okay. Now we'll try to implement them in our models. Okay. Now basically I'm just showing you how gradient descent is useful and how this backward pass is implemented. Okay. See, I created an array 3, 2. Okay. And then what I did is what I did is I took this array and I just added 10 to it. Okay. So as you can see here, this was the first thing. This array was created. Okay. And then I added 10 to it. So this was the output. Okay. One thing you should see here, this is some new thing that we have wrote in the AND function. This is required gradient equal to true. Basically, what we are doing is we are now starting to track. We are tracking the gradients. Okay. So suppose what I'm saying here is, suppose see I want to correct something. Okay. Suppose I want to correct z. Okay. So I have to correct x and y. So for that I should know now what was the x value, how x value was, what was the y value, how the x value, y value was. Suppose there are many more neurons here. So I have to go back till that neuron, to the last neuron, to correct things from there. Okay. So for that I need the gradients. Okay. So we need the gradients for that. So where's this also we have to use this required underscore grad equal to true. So what it does is it basically stores the computation graph in it. Okay. So see, what I did is basically in simple words, it stores the history. Okay. So I declared x, added 10 to all the values of x, I got y. Okay. Then I did y cross y plus y, I got z. Okay. Then I calculated z, I got w. So finally, when I got w, this is the value of my w. Okay. So see, here every time I'm computing some operation, it is giving gradient function add backward 0, multiplication backward 0. Basically, this is saying me that I am doing this is function. This is keeping the note of this is function. So it knows that this is functions had took place till coming till this point. Okay. Now suppose I want to suppose I want to correct something. Okay, I want to change the gradient backward. Okay, so what I will do is I will use a backward function. See how it is used. I declared a 2, 4 random tensor metric x I got. Then I added 2 to every value. This I got. This was the first thing I got. Then I got y, I added 2 to all. So I got add backward. Every value was added to 2. Then I calculated z equal to y of mean. So I got this single value and I printed this value. That is this z. Okay. And then what I did is I used z dot backward. So see what exactly here happening is I made a forward pass. This was a forward pass. This first this is to just I printed. Then here I made a forward pass. What is the forward pass? I perform some operation. I perform operation as y plus x plus 2. So see here I did. I had x. Then I did some forward pass. I did some function x plus 2. Then I again did some function. I got mean, and then I calculated loss. Now I have to correct some. I have to decrease this loss. So what I will do is I will try to correct this. So this is giving me the grade. Then to do that, I will use x dot grade. So what x dot grade will do is it will give me the values of this array which must be, so that I will get the minimum loss. Okay, so I got this as a backward gradient backward. Okay, one thing to note here is, see here I did y dot mean. Okay, when I did y dot mean, I got a single value 1.7314. Okay, so if suppose there is no there we don't get a single value, but we get 2 or 3 values in it. Basically, if we get a tensor of 2 dimension or 1 dimension in it, okay, but not with a single value, then for that we have to in backward also we have to pass same size of tensor in it, 2,4. If I suppose my z was something 2,4, then I have to pass 2,4 in my backward too. So then it will be easy for us to calculate the gradient. Okay, so see, I made a forward pass of add backward, then I made a forward pass of multiplication, then I did z backward. I computed all the backward things. I computed all the backward passes, and then I got x dot grad. Okay, then I got the gradient with respect to x. Is this clear? Is this much part clear? Is there any doubt with this much part? Okay, I assume no, not till this much part. Okay, so there is one more function, that is dot detach. So see what we were doing here is we was in here when we put it required underscore grad equal to true, we were storing the history. Okay, what are operations we are performing. But suppose at some point you don't require certain things to be in your computation graph. This is certain things that were pre-processing like things. Okay, which you don't want to be reflected in your computation. What you can do is you can use dot detach function or with dot no underscore grad function. Okay, so what I did here is I made an x with required grad equal to true. Then I took y. I wrote y x dot detach. So what I'm doing is here I'm copying the values of x in y. I'm just copying the values. Okay. And then other thing that I did is torch dot no grad z equal to x plus 1. I'm adding values of 1 into z and then I'm printing it. Okay. So see, first of all, I got this print x. I got this print with required grad equal to the same value I will get here, but this time the required grad is false. So basically, this thing will be not saved in the computation graph. And similar thing I'm doing with torch dot underscore grad no grad. Basically, even same thing will happen here. I'm just adding value of x, value of 1 in x, and then I'm printing the output. See, this is how the output is printed. Okay. Now, as I said, many times you want to flush the gradients out. So what these gradients were? These were what we were doing in backward pass was we were taking the loss that we got. We were computing the derivative of the loss with respect to the weights. Okay, and then we were tuning our model. So how we do this is we pass batches. So what we do is we divide our data set into batches. We pass the batch one, the things, the model learns something from it. Loss is calculated, gradient descent is done. It comes to a certain point. Now the next batch is given. Okay, but if before giving the next batch, what should I do is I should zero the gradients. Basically, that metric of gradient must become 0 for second batch to learn from the second batch. Okay, if it is present, if the first batch some values are present, that might affect the output of the second batch. Okay, see, this is something like this which will happen. See, this is 2 4 torch time function. I printed it. I put required gradient equal to true, and I'm not flushing here. Okay, so see, I first calculated y that is equal to x plus 2 dot mean. Okay, so I just did x plus 2 and I calculated the mean and did y dot backward. So see what happened here is this is my first thing, that is x. This whole is my x. Then I calculate, oh, this the cell got ranked. Just a second. I need to say. Yes. So, yeah, just a second. Yeah. So see, this is my X. This part is my X. Then this is the first thing that this is the first iteration. There are 3 iterations in it. So this is the output of the first iteration. This is the output of the second iteration, and this is the output of the third iteration. So this is the output of the gradients, and you can see that it is just getting added up or something happening in it. Okay, so this is just getting stored in it. We are not flushing that out. So it will not give us the correct results. And see here, after putting the flush dot grad dot zero, what happened is, see, this was my gradient first, then my gradient dot decrease, then my gradient dot decrease. Okay, so as you can see here, my gradient is decreasing. Basically, I'm coming down towards this graph. I'm coming to the minimum point. Okay, and before in that, what was happening was it was not decreasing. It was increasing, increasing, increasing. Okay, so it is important for us to flush out the gradient. Okay, so this is the this was about gradient. So now I will implement a small model. I will show you how small model in Tensor works. So is there any doubt till here? Is there any doubt till here? I assume no doubt, so I'll move ahead. Just a second. Yes. So now we'll start with a model, simple model. So suppose I want to create a linear regression. Okay. So what I'm doing is I'm passing x and y to tensors. Y x is my input and y is my output. X has 10,5 as an input and y has 10,5. Okay, as an output. What I'm going to do is I have to pass weight, that is a W, which is I'm assigning as 1, and my bias, which is 1. Okay. We all know the formula for linear regression, okay, which is y underscore predicted equal to W into X plus C. Okay. So what I have to learn here is I want to learn here what my value of W must be and what my value of C must be to get the y predicted equal to the same, y predicted equal to y true. Okay. Basically, the loss must be 0 between them. Okay. Theta dot equal. But now see what will happen. So first is my forward pass, which I defined. My forward pass is I must calculate W into X plus B. Okay. Then I gave number of epochs I want. That is 100 epochs. No epochs. Yeah. So one more thing. What is epochs? See, epochs is how much times I must look to your whole data set. Suppose I had a data set of 100 images. I divided into batch of 10. So I got 10 batches. One epoch means looking all the 10 batches. Second epoch means looking again all the 10 batches. So why we do this is to decrease our loss, to learn. Okay. So my epoch is 100. My learning rate is 0.001. All you know what learning rate is, this amount of steps as we want to take. Then I for that then I gave a range for range. Then I made a forward pass. So basically, y equal to forward of X. I took value from X, that is X, and said I took first 10. Then I calculated weighted value. Then I calculate loss. So we talked about this before when I was giving you what are different types of loss. So this is MSE loss, that is mean squared error loss. What this will do is it will take the predicted value, it will take the true value, it will give out the difference of squared of the value. Okay, this mean of square of loss. Okay, mean of the square. So what it will do is it will calculate the difference between the predicted and true value. It will give out the mean square loss of it. Okay, so we got the loss. Then what we'll do is we will calculate the gradients backward. So we calculate the gradients backward. Okay, and then what we'll do is we will change our values. We will change our input values, our weights value. Okay, so now what we'll do is we'll tweak it. How we will change it? So there are two ways: either do it manually or to actually use the optimizer function. So see, this is how manually we are doing. We are calculating a gradient with respect to W. Okay, then we are multiplying the training rate and we are changing the W. So the new W will be the difference between the old W on the and the learning rate into W dot grade. Okay, and B will be difference between the learning rate into B dot grade. Okay, so this is manually weird. But suppose I want to do it automatically, so we have optimizer functions here. So here we are using stochastic gradient descent. This is SGD, stochastic gradient descent optimizer, which is from the type of gradient descent optimizers. Okay, so what I'm doing is I am optimizing W and B, and I'm giving the learning rates. Okay, so it will optimize my W and B. Then I did this optimizer step. I just do this. Here I called the optimizer step. Here I did the optimizer step. I performed the optimizer step, and after that I flushed out the gradients. Okay, so this all happened in my one iteration. Okay, such 100 iterations I'm doing, so I'm learning. Okay, So see here what is happening. In my on my zeroth epoch, my the loss was 1. Basically, the loss is 1. Basically, it didn't learn anything. Okay. Then see the loss got 0.15, then the loss got 0.10, then 0.9, then 0.963, then 0.957, then the loss got decreased, and in the last 100th iteration, the loss was 0.0934. Okay, and the value predicted from my tensor was 9.8 and 5.3. Okay, and my true values were 10 and were 10 and 5. Okay, so you can see here how I made a simple linear regression model using the knowledge that we acquired, and it gave us a good decent output. The number of epochs were less, and the data set was also less. So with just two values in our data set, we got this loss of 0.09. Okay, so is this much clear what I did? I will explain this again once again. So I made two tensor dimensions, x and y of one dimension, 10,5 and 10,5. I declare my W and B. Basically, my equation is y equal to mx plus c. Here my equation is y equal to wx plus b. Okay, this is my equation for this. Okay, then define the forward path. This is wx plus b. I gave learning rate and epochs. Then I predicted the value of y. How I predicted? I just passed x in forward definition forward. So I got predicted value of y. After predicting the value of y, I calculate loss. I calculate loss predicted minus the real value. So how that is done? That is mean squared loss. That is not directly minus. It is minus of mean square value. Okay. So I got the loss. After see here losses is the real y and the y beta. I got the loss. Then I calculate the gradients backward. Okay, I got the gradients backward. Then I optimized. I changed the values of w and b. So in such a way that I must decrease my loss. I performed the optimization step. I zeroed down all the gradients basically. For the next epoch, it will learn things. Okay, and then I ran my model. So after 100 iterations, I got 0.0934 as my loss, and the predicted values were 9.8 and 5.38. Okay, and my real values were 10 and 5. Okay, is this clear? Is this much clear? Is this whole model clear? So in this everything in this we use tensors also, we use backward and forward classes also, and we understood gradient descent also. Is that much clear?
Yeah.
Okay. Now we will go towards linear logistic regression. Okay, so this was linear regression. Now this is your homework exercise. Now this was just simple. I just had two data points and I just was playing with two data points. So now, okay, just. So now in this is the homework for you. First, this is a linear regression. So there is a data set of samples of 100 100 things in it, data points in it. And then what you have to do is you have to design model. There are many things given in it. You have to train, you have to explore how backward pass, how forward pass works, and then you have to see things. Okay. Now, due to time constraint, I will directly move to the logistic regression. Now, what is logistic regression? We'll see that. First of all, what we'll do is I will take the wine data set. There is a wine data set. I directly imported data set from this. There is library. I directly took the data set dot load wine. So I got the wine data set. So what this wine data set has it has three classes. It has number of attributes, and on the basis of that attributes, it defines what type of wine it is. Either it is 0, which is which is class 0, which says that the wine is just a second, which says the wine is even maybe written. Yeah. So yeah, yes. See, these are the features name. Just I will show you the feature name. So these are the different features: alcohol, malic acid. As on the basis of this all features, we want to define the wine in three classes. Okay, and the three classes can be 0, 1, and 2. The 0 class says that the wine is not good. It is the one says that it is moderate, and the second say it is very good quality of wine. Okay, so what I will do is I will divide the data into target and the training set. Okay, so see x and y data and data target. Okay, so as you can see here, the shape of the data is 170, 13. 13 are features, 13 features that I just showed you, and my target is just 178, comma. Okay, so one thing I want to ask you here, it is just comma. If I want to add one dimension here, which function that we learned today we can use? Can anyone answer? We learned a function today which will add one dimension here in this location. What was that function? Sorry, I didn't hear you. Can you please repeat?
Unsqueeze.
Yeah. So we will put unsqueeze function here. So what we can do is instead of dot reshape, we can just directly pass unsqueeze function. So our y will become while there will be one more dimension of one added to it. Okay. So basically what I will do is I will take these 13 features. I will make my model learn, and then I will give one output data, whether which class it belongs to, whether it class belongs to 0, 1, or 2. Okay. So for simplicity, what I will do here is for your for logistic regression, as we know, logistic regression basically based on it very basic level differentiate between two classes, 0 and 1. So what I will do is I will delete the class. I will delete class 1. I will change all the class to as class 1. Okay. So in this operation, what I did is I deleted all the data points in the data set where the value was 1, and I changed values of 2 as well. Okay. So we have now two values, 0 and 1. Okay. So this is my new shape. This is 107, 1 and 107, 13. Okay, so I deleted all the values which were one in it. Okay, so then what I do is I split the data set in my training and testing set. Okay, so this is my x10, x-test, y10, y-test. Okay, which we'll see how we use it. So I split it in size of 0.1. That is 10%. 10% is for training set, sorry, for testing set, and baki and other 90% for or for training set. Okay, so my training is 96 and my testing is 11. Okay, 96, 96. Okay, in this way I split it. Okay, now what function? And now this is function. This function is called standard scalar. So I'm going to use this function in my train and my test. Okay, both to transform my train and test values. So see what this function does is, suppose I say you to predict the value of a house. Okay, and on the value means give rating to house. Okay, and that rating to house depends on size of the house, number of bedrooms of the house, and exact. Okay, now assume that the value of that the price is in crores. Okay, and the number of bedrooms are single digit values. Okay, so what will happen is your ML model might overpower this bedroom and it might neglect this bedroom. Okay, so what we do is we use the standard scalar. What this standard scalar will do is it will try to bring all the value in the range of 0 to 1. So for bedroom also it will be in the same range, and for the price also will come in the same range. Okay, did you understand what I'm saying, what I'm doing here in standard scalar? So I'm just fitting it. I am just fitting exhaust in and exhaust test. Now what I will do is I will try to predict. I will make my model. Okay. So here it was a NumPy array which was there first. So I just converted a NumPy to torch, a to tensor using torch dot from underscore NumPy, which we learned before. So just a glimpse of what this our logistic regression looks like. You have two inputs. Okay, we have a neuron. And on the basis of two inputs, we give output. And how the output is given is there is some threshold value. And if the value is greater than the threshold value, the class is 1. And if it is less, then the class is 0. This is a sigmoid function. We use the sigmoid function to give the output of it. Okay, this is the sigmoid activation function which we use in the output here. Okay. So see how one more Python thing that one more thing of Python that I want to demonstrate here is, see, I made a class of SMLRA. I passed x equal to 100. I passed the definition int function in it. I passed 100. Okay. Now when I print x, I will get 100. Basically, without initializing the class, we can input a class exactly without initializing the class. Okay, so we got 100. Okay, and when I made an object out of it, I made an object a equal to SNRA, and I printed a dot x, then I got 200. Okay, so this thing is also important because when we make models ahead, we are going to use it. Okay, now see, what I'm doing is I'm making a logistic regression model. Okay, so I define an init method in which I just call this logistic regression, and then I made a linear layer. So this was a neuron here was a linear layer neuron. Okay. So see how the layer is made. Number of input features, comma 1. Okay. So what is the input first? We must understand what this input is. The input is number of input features, comma 1. What this is basically how much inputs I will get and how much output I will give. So I had 13 inputs, so I will get 13 lines here and I will give one output line. Okay. So it is like that. Okay, so it is 13, comma 1, and it is linear function. We saw there are different types of layers we can add. So this is a linear function layer. Okay, so it says that the output size is 1. Okay, which is the output size is 1, and the output will be between 0 and 1. Okay, as it is a logistic regression. And what we have to do is we have to do in forward passes. We have to just pass that values into sigmoid function, and we'll get the y weighted value. Okay. Now we just call the model equal to logistic regression. This model I just called it. I just declared my optimizer and losses. My learning rate is 0.01, epochs are 100. Now here the loss is binary cross entropy loss. See, why I'm using binary cross entropy loss? See, I have to deal with binary values 0 and 1, and I have to find the cross. I have to find the loss in it. So I'm using binary cross entropy loss. Okay. Then optimizer. As we discussed about optimizer, what optimizer does is it tweaks your weights. It tweaks your weight. This line weight. It will tweak this weight. So this optimizer here, the optimizer we are using here is as it is stochastic gradient descent. The same thing we are using, and then we are training it. See how we train this. We first make a forward pass, then we make a backward pass. We update and we zero down. So a forward pass by underscore predict model x dot train. I made a forward pass. Then I made a backward pass. I compute the gradients. I optimized. I called the optimization function. I zeroed out the gradients and then again did the same thing. Okay, for a number of epochs, and then I printed out the value. So as you can see here, the loss is decreasing 7, 7, 6, 2, 5, 1, 4, 3, 37, 32, 28, 26, 23. Okay. So in this way, it came down. Okay. Now this is basically the computation graph which was happening here. We had 13 features in input and one output. We accumulated the gradients, we did backward. So this was the thing which was happening. This is the whole graph. Required gradient equal to terminal input. This is the whole computation graph which is saved in it. It knows what step it has did, so it can track backward and give the output. Okay. So this is the computation graph. We first did accumulated gradient, we did backward, we did t backward, then we did and backward, then we did use the seg model function, and then we got the output, something like that. This is basically a computation graph which is stored. So this is just testing. We as we see, we just ran the testing thing. So our model gave us almost 100% accuracy. The model was 100% accurate. This is a confusion metric. What confusion metric says is I paid the value true and it was actually true. So such we had 4 values. Okay. Then confusion metric says I painted value negative and it was actually negative. It was I painted negative and it was actually negative. That is 2 negative. So this was 6. Okay. So it get 4 zeros or 6 4 0 6 or something like that. Okay. And there's one thing which is here and we got one here. What is it is it says the painted value was positive, but the actual was negative. That is actual value was something 0 and painted was 1. So that's why we got approximately 97% of accuracy with our model. We can ahead increase our model accuracy as we more train, as we give more asset to it. So is it clear? Is this clear? Is this clear how we made a logistic regression model? Is there any doubt? Okay, so is there any doubt in general to all things that we saw? See, it is really tedious. It is little tedious to understand if you're learning this all first time. What you have to do is you have to just stick to the basics. You have to just see how the way we came. We first made tensors, then we made tensor operations. Then we saw forward pass, backward pass. Then we saw optimizer function, how it is used. Then we made a simple linear regression model. Then we made a logistic regression model. Okay. So now what I will do is, if you don't have any doubt, I will call upon Alekya to start with neural networks. Alekya, can you please start?
Yes, I'll start it. Okay, so is my screen visible?
Oh, yes, Alekya.
Okay, so hello everyone, this is Alekya, and I will be explaining the theory behind neural networks, what is gradient descent, what are activation functions, the different types of activation functions, and then how do you train a neural network, and at the end, we'll take a look at a simple code. So a neural network or an ANN are basically computational systems that mimic how the human brain works. And ANN is a subset of ML and is at the heart of deep learning algorithms. It solves common problems in AI, ML, and deep learning, such as extracting features, classification, clustering, and speech recognition. And one of the most well-known example is in Google's search algorithm. So, just a second. Yeah. So a neural network basically has 3 types of layers: the input layer, the hidden layer, and the output layer. So this is the input layer. These are the hidden layers, and this is the output layer. Okay. So the input layer is where we feed our neural network all the features, and no type of computation takes place in this layer. Only the features are passed on to the next layer. And then we have the hidden layer. This is where most of the computation takes place on the features inputted to the neural network. And after this, the result is passed on to the output layer. And the output layer is where we can see the result learned by the neural network. Now, every node in a neural network is connected to a node in the next layer via some weights. So for example, this node is connected to this node, so on by some weights, Just a second. Okay. Yeah. So these arrows are, some weights. Okay. So every neuron is associated to the other neurons in the next layer via some weights. And every neuron also has an associated bias to it. So if the output of a neuron is above a specific threshold value, then the data is passed on to the next layer, or the data isn't passed on if it doesn't cross the threshold value. So that is how the data is propagated through the neural network. Okay. Yeah. So a neural network relies on training data to learn and improve its accuracy over time. And once these algorithms are fine-tuned for accuracy, they can be used as powerful tools in computer science and AI. And tasks in speech recognition or image recognition can take minutes versus hours when compared to the manual identification by human experts. Now, what is an activation function and what are the different types of it? So an activation function decides whether a neuron should be activated or not by calculating weighted sum and further adding bias with it. Okay, so the purpose of an activation function is to introduce a nonlinearity into the output of a neuron. So let's consider some activation function, and it takes the input as the input features multiplied by the weight and adds some bias to it. And then it generates some output. So if this output is above a specific threshold value, then the data is propagated or it isn't. So this is how an activation function helps us. Now, there are different types of activation functions. Firstly, we have a linear function. This is the equation y is equal to ax, and this is the graph for it. So the range is minus infinity to plus infinity, and it's used at the output layer. Then we have sigmoid function. And this is the equation for it, 1 upon 1 plus e raised to minus x. The range for this function is 0 to 1, and it is used in the output layer of binary classification, since the result is either 0 or 1. And the result can be predicted to be 1 if the value is greater than 0.5 and 0 otherwise. Then a slightly modified version of the sigmoid function is tan hyperbolic. So this is the equation for it, and this is the graph of it. And as you can see, the range for this function is minus 1 to 1. And this helps in bringing the mean closer to 0. And that's how it makes learning easier for the next layer. Then we have ReLU function, which is this is the most commonly used activation function. And the equation for this is max of 0, x. So this means that if the input to this function is a positive number, then that is the output itself. And if the input is a negative number, then the output is 0. And ReLU is computationally less expensive than tan hyperbolic and sigmoid because it doesn't use any complicated mathematical operation. And that's why it learns faster than the other activation function. So now let's understand how do we train a neural network. So there are two parts in training a neural network. First, we have forward propagation, and then we have the backward propagation. So let's consider a simple neural network. So this is our input layer. This is the hidden layer, and this is the output layer. So our input layer consists of m neurons, okay? And the hidden layer has 1 neuron, and the output layer has 1 neuron. So the input layer is where we'll be feeding all our input features to the neural network. And then every neuron in the input layer is associated to the neuron in the hidden layer by some weight. So W1, W2, and so on till Wn. Now this hidden neuron has a bias associated to it. Okay. And then we can choose an activation function. And that activation function is going to take in the input as the input features multiplied by the weight and adds a bias to it. And then it generates an output, and according to that, we get an output value. So this is what happens in forward propagation. Now we have backward propagation. Now what happens in forward propagation is that since the values of weights and biases were randomly initialized, it's obvious that the output of the neural network wouldn't be accurate. So what do is that we compare the output value and the actual value, and then we get the difference of it. So yi minus y hat, and y hat here is the calculated value, and yi is the actual value. So we take the square of the difference and then the mean of it. So this is called the mean squared error method. Okay, so this function is called the cost function and denotes the loss of the neural network. Now we backpropagate this loss and update the weights according to how much are responsible for the error. Now our main aim is to increase the accuracy of the neural network. That is, we need to reduce the loss. That is, we need to find appropriate values for weights and biases such that this loss is minimal. So how do we calculate these appropriate values? So we have an iterative algorithm called gradient descent, which finds out the global minimum for a function. So let's assume this graph to be of our cost function. Okay. So at the beginning, I have chosen some random values for weights, right? So let me consider this value for W. So my yi. So at this point, I would be getting some slope. Okay. So I'll measure that slope. And if this derivative is positive, then I decrease the value of W. Okay. And if suppose my value of W was somewhat negative. Okay. So what I do is that I increase the value of W. So in this manner, after a number of iterations, we would reach to a value of W where the slope is 0. That is a derivative is 0. And that would mean that we have reached the global minimum. And this value of W would give us the least loss. So there's a similar process for calculating the appropriate value for biases also. Okay. Now we need to have a factor by which we can increment or decrement the biases and weights. So that factor is called the learning rate. So if the value of learning rate is too small, then we might, never reach the global minimum. And if the value of the learning rate is too large, then we might miss the global minimum. And you can see we could be just bouncing here and there. We would never reach the global minimum. So that's why it's really necessary to choose an appropriate value for learning rate. And the best approach to see is that to decide a value for learning rate is that you can take multiple values for it, like starting from 0.1 and then going to 0.01, 0.001. And you can see which value gives you the least loss. So that's how you decide the value of learning rate. Now, since we have covered most of the theory required to understand how a neural network works, we'll just go through the overall training process once again. So first, we just randomly initialize the weights and biases to some small numbers closer to 0. And then we give our neural network its input features. Then we perform forward propagation, where the neurons are activated depending upon the weights. And then we calculate the error. And then comes back propagation, where we back propagate this error, and the weights are updated according to how much are responsible for the error. And then we minimize this error using gradient descent. Okay, so now let's go to the code. Okay, so yeah, so first let's just import torch, and then this is my input tensor. Okay, X is the input tensor, and we can see the number of features using X dot shape 1. So the number of features over here is 1. And then this is my output tensor. So 1, 1, and 0. So just a second. Yeah. So this is the input, this is the output, and this is the number of features. So my aim over here is to construct a neural network such that my output value would be close to this value. Okay. So now I'll choose choose any activation function. So I've chosen here the sigmoid function. This is the expression for it. Then this is the derivative of the sigmoid function. Okay, this is the expression for it. And this derivative function would be useful in back propagation. Now we need to initialize some variables. So first, epoch. So this is the number of training iterations. Now I've set that to 7,000. Then we have learning rate, which is set as to 0.1. Now we need to decide the number of neurons in each layer. So over here, I'm taking a very simple neural network having 3 layers. the first layer or the input layer has 4 neurons. It's X dot shape 1, which is basically 4 neurons. Then we have the hidden layer, which has 3 neurons, and the output layer, which has 1 neuron. So our neural network looks something like this. Just a second. Yeah. So we have 4 input neurons, 3 in the hidden layer, and 1 in the output layer. Okay. Now we need to randomly initialize our weights and biases. So there's WH and WOut. So now what are these? So WH corresponds to the weights of this layer. Okay. So now, as you know that every neuron in a layer needs to be connected to the neurons in the next layer via some weights, right? So this neuron is going to connect it to this neuron, similar to this neuron, and so on. Okay. So we have 4 neurons over here, and we have 3 neurons over here. Okay. So total number of weights required would be what? 4 into 3, which is 12. So we need 12 random values per weight. So we generate those random values using torch.random. And this is going to generate a matrix of random numbers having dimension input layer neurons cross the hidden layer neurons. So input layer neurons is over here 4 and hidden layer 3. So 4 cross 3. So it's going to generate 12 random numbers of type float tensor. Similarly for biases, we have 3 neurons in the hidden layer. So we need 3 biases. So we again generating a matrix of dimension 1, 3 of type float tensor. Now W out and B out, these values correspond to weights and biases of this layer. So again, we have 3 neurons in the hidden layer and 1 neuron in the output layer. So you would require 3 weights, okay, and 1 bias since there's only 1 neuron in the output layer. So for W out, matrix of random numbers having dimension, hidden layer, comma, the output layer, output neurons. So this is P, comma 1, and this is B out, and number of output neurons is 1. So this is going to generate 1 value for B out. Now our values are initialized. So let's train the neural network. So first, what do we do is that after giving input to the neural network, we know that we have an activation function, and the input for the activation function would be the input features multiplied by the weights, and then we add a bias to it. So over here, we're using torch.mm to multiply these both values, x and wh. This is hidden layer input 1. And then you add bias to it. And then you pass this hidden layer input into the sigmoid function. So you get your activations. Okay. After this, so at this point, after these 3 lines of code, we have generated activations at this layer. Now, we will repeat the same process to calculate our output. So again, we're going to treat this value as our input, multiplied with the weights, add the bias, and then pass it into the sigmoid function. And we are going to generate an output. So we got our output. Now we need to measure the error and then backpropagate it. So the error would be y minus output, where y is my actual output, this. Okay. Now I would calculate the slope at the output layer and slope at the hidden layer. Okay. After this, d output would be error multiplied by the slope of the output layer. And error at the hidden layer will be the product of d output and w out transpose. So this is because we're going in the reverse direction. That's why the transpose. And then these 4 lines of code, this is where our weights and biases are getting updated. So W out and B out. So first we're going to update these values. We're going to update the weights and biases in this layer and then in this layer. So after this, yeah, so you can see the output of the neural network. Okay, so we can see that the predicted value is very close to the actual value. But what if I just reduce the number of epochs to a very low number? So you can see that the output isn't accurate. So it's really important for you to train your neural network over a large number of iterations to have correct value of learning rate, to choose the best activation function according to your needs. So that's it. This notebook is also available on SMLRA's GitHub.
Alekya,
So
yes.
yeah.
Now questions for you all guys. Yeah, Alekya, just be there on that block of the code. So in back propagation, can you go on Alekya on the W out, where the W out is? Your last code.
This one.
Yeah, just have the full, right? Yeah, so we saw a function today. So we saw a direct function today which can do all these 4 lines of code in just by using that. We can just call that thing. Can even say what was that? We used something in our previous course where all the 4 lines that we wrote now can be just done in 1 line. You all guys can recollect what it was. Anyone? Okay, so I will give the answer. It was optimizer function. We used stochastic gradient descent as an optimizer. So it was directly operating these things. This all the 4 lines that she has wrote was done using that single line. Optimizer equal to optimize dot stochastic gradient descent w comma b, in which this all things were getting updated. Okay, and one more question. Here before that 4 lines, she has calculated the loss. So do you guys remember any type of function that we use which was giving the loss directly instead of all 4 lines in the top 4 lines that are written? Anyone? Okay, so I will give the answer. It was in the previous ones you used the mean squared error loss. Okay. And here she is using simple loss equal to y minus output. Actually, she is subtracting. So here is just she's difference. She's just finding the loss difference between the losses and difference. Is that clear to all? Is it clear now?
Yeah.
Okay. So is there any doubt from anyone's side? Anyone understanding anything now?
No.
So I hope this much things were clear to you. What tensor is, what tensor basic operations are there. I will recommend you to go today and try these notebooks out on your own, to explore on your own what are different optimizer functions, what are different loss functions. And in the tomorrow's session, we are going to deep dive. Tomorrow will be a little advanced session in which we are going to deep dive into convolutional neural networks and text summarization. Okay. So in that, many things will be happening, which will be a little more towards a more advanced level. So it will help you all to do your projects too. So please look into today all the things that we did today. Run all these notebook ones. Okay. Is there any doubt? Okay. So with that, is there anything other? Is there anything to say, Alekya, Kedar, Himanshu?
Nope, that's it.
Okay.
No.
So with that, with that, we'll stop our today's session.